Hello and welcome to the Scholar Circle, scholarcircle.org. I'm Maria Armoudian.
The legacy of Stephen Hawking and what he's meant for our understanding of the universe.
We are joined by two experts. Priya Natarajan is a professor in the departments of astronomy and physics at Yale University. Her publications include Rapid Growth of Seed Black Holes in the Early Universe by Supra-Exponential Accretion and New Observational Constraints on the Growth of the First Supermassive Black Holes. Peter Galison also joins us. He's a professor in the Department of Physics and director of the collection of the Historical Scientific Instruments at Harvard University. He's the author of How Experiments End, Einstein's Clocks, Poincare's Maps, and Image and Logic. He's also the co-editor of Einstein for the 21st Century, His Legacy in Science, Art, and Modern Culture, and the co-director of the documentaries Ultimate Weapon, The H-Bomb Dilemma, and Containment.
Welcome to the Scholar Circle. It's great to have the two of you here with us to talk about and put the work of Stephen Hawking and his legacy into the context of physics and what he has meant for us. Peter Galison, I thought we should start with you, given the work you've done on the history. So if you were going to put his work, his contribution, our understandings about the universe into a historic context, how would you help us understand that role?
When Einstein first developed his general theory of relativity in the midst of World War I in 1915, and then it was confirmed by the measurement of the bending of starlight just after the end of the war in November of 1919, Einstein became the most famous scientist in the world by far, really the most famous scientist since the time of Darwin or Newton. And that theory became a model for what science was. It was Einstein who, in some sense, displaced Newton and changed our view that space could actually be bent in important ways. Almost immediately after Einstein published his paper, a friend of his named Karl Schwarzkopf discovered while he was at the front fighting in World War I that there was a solution to Einstein's equation that predicted what eventually became known as black holes. So it was many years before that was taken seriously as a physical thing. What Hawking did was to help us understand how black holes fit into the wider structure of physics, how it connected the great development of relativity with the astonishing revelations of quantum physics that was developed in the 1920s. So Hawking was a figure of unification in some ways, but also someone who opened up problems that are still today being much debated.
Now, Priya, you have said to me before we started recording that Hawking's contribution was really more on the theoretical basis rather than the actual measurable basis of black holes. Can you explain to us, lay people, non-physicists, what exactly you mean by all that?
So just as Peter mentioned, the black hole solution is an exact solution to Einstein's field equations, and it describes this shape of space around a compact mass, a black hole. And in the real universe, we do see black holes, astrophysical black holes, that correspond to the end states of stars. So these are real objects in the universe that have the properties of a black hole solution, but we actually know that they exist because we can indirectly map their existence. And so I think where Hawking's work fits in is that he was trying really hard to understand the fundamental nature of black holes and the nature of the sort of sacred boundary that black holes have called the event horizon. And this is a boundary around a black hole which encases a singularity. So basically it's a place where all known physical laws break down. But this region is basically a point of no return. And so any phenomena that reveal the existence of the black hole have to occur outside the event horizon. So in astrophysics, we are constantly looking for regions of space-time that have the intense gravity of a black hole, however, whose presence we infer from the impact of either the bending of light around the strong gravity by a black hole, or by the impact on motions of particles that are in the vicinity. For example, we know that quasars, which are the brightest beacons in the universe, these objects that outshine the galaxies that host them, are actually powered by supermassive black holes that have masses in excess of 1 billion times the mass of the sun, while they're feeding gas. And so gas, as it is sort of lurching towards this event horizon of this supermassive black hole, gets heated and starts to glow in the X-rays. And so that's how we've sort of inferred the presence of these monster black holes in the universe. However, we still don't understand what's really going on at the event horizon. And Hawking's work was really trying to understand, I just told you that it's a point of no return, and what that really means. Do you actually lose all the information about whatever went in and crossed the event horizon? So there are many puzzling fundamental problems that have to do with conservation of information. So do you lose all information about what went into a black hole? Can you ever retrieve it? Can you recover it? So these are very fundamental questions that we as astrophysicists can skirt, because we are looking at the impact of a black hole, how the presence of a black hole shapes the properties of the galaxy it's sitting in the center of, and so on. But, he had a very, very nice sort of analogy to what is a fundamental problem. It's called the information paradox, which is what happens to information if it crosses the event horizon. And the analogy that I really like, it's like, you have an Encyclopedia Britannica and you look up the capital of India and it's New Delhi, and then you burn the Encyclopedia Britannica, keep all the ashes in a box, so nothing has left this box. So the information that New Delhi is the capital of India is still in this box. It's in the ashes. We don't know how to recover it, and we don't know how it's saved. So, Hawking used this analogy, beautiful analogy, to describe what's really likely going on inside the event horizon of a black hole. And as I said, astrophysicists and astronomers, we have the liberty of just sort of looking outside and looking at the impact of black holes rather than really trying to understand the mathematical nature of black holes.
So let's back up just a little bit. And Peter Galison, maybe we bring you back in here. There is a significance of black holes that's related to really the origin of the universe. What is this origin? What is the significance of black holes?
Well, black holes are the most extreme objects that we know of. They're the most densely packed amount of mass that you can have. They seem to raise questions about the tiniest forms of matter and the singularity that Priya mentioned at the center of a black hole looks like where space and time might be so extremely bent that you actually might create something more fundamental than space and time, where string theory becomes important, or where there's a kind of foaming aspect of space and time that we only see when it's spread out enough to look smooth to us. So it raises questions at the tiniest, most extreme parts of nature. At the same time, these supermassive black holes that Priya mentioned, like the one that's 4.5 million times the mass of the sun, the center of the Milky Way, or other ones that are billions of times the mass of the sun, actually shape things the size of galaxies and even bigger. So they seem to be objects that range in their effects in the world from the most microscopic scales of physics to the large-scale structure of things as big or bigger than galaxies. And that's really astonishing. Hawking has helped to advance our understanding of trying to put these different scales and effects together.
You mentioned string theory, and for those of us who are not physicists, how can we understand that?
Well, we've thought for a long time that the most fundamental objects in the world were tiny particles that also might act in some experiments or observations as waves, but they could be thought of as hugely smaller than a BB, but like particles. And an idea that's arisen in the last couple of decades that's still a fundamental interest to theorists is that maybe the most fundamental things are not like little BBs, but more like little strings. And the vibrations of those strings, like the vibrations of the strings plucked on a violin, could correspond to different energies. And those different energies, by Einstein's famous equation E = mc², might be more energy, might actually act like the particles that we see of different masses. So the idea of string theory was that maybe the basic things were little strings and their vibrations differentiated this little string into the different mass particles that we observe. So it was a way of unifying the world and unifying all the different kinds of particles and different kinds of forces, that everything was simply different excitations, different vibrations of this basic string.
So, Priya, you've been really building on Stephen Hawking's work on black holes. You worked on the formation of black holes. What have you found in terms of black hole formation?
What was very clear is that one way to make the first sort of seed black holes is provided by nature as the end states of stars. So when the first stars formed in the universe, and if they happen to be above 10 times the mass of our sun, then they would burn up all their hydrogen and helium, exhaust their nuclear reactors, and explode and leave behind a little black hole. Of course, it's quite uncertain what the masses of those initial stars were, but we have every reason to believe that in the very early universe, in the pristine universe, the first generation of stars to form were likely more massive than the generations that we see around us assembling right now. So it's quite likely that you formed massive stars, and most of them likely ended their lives leaving little black holes. But the puzzle then is, how do you start from a little remnant, which is maybe a few times the mass of the sun, and how do you grow it to 1 billion times the mass of the sun, that too extremely rapidly in the early universe. And the reason for that is that the time when the first stars switch on in the universe and the time that we are starting, we're inching and looking further and further back and discovering these quasars, these bright beacons that are powered by supermassive black holes already in place. So we're starting to come up with a timing crunch of, how could you really grow these little seeds to make the monsters that we see? And so that's where a lot of the work of my research group and my work has been focused on, trying to come up with other viable ways to make the first black holes, and in particular, ways to make them much more massive from the get-go, so that you don't have as much of a timing problem to grow them into sort of the billion solar mass behemoths that are powering the quasars that we are seeing for sure. So, we came up with an idea about 10 years ago, 12 years ago, called direct collapse black holes that form in very rare sites in the universe, which from pristine gas. And so we sort of developed a whole kind of machinery of understanding where spatially in the early universe you could form them, and therefore what are the potential observational signatures that show that you could have this additional new channel for making black holes. And a decade later, when we're finally able to do the kinds of simulations on a computer that can replicate the physics, we find that these are viable and are potentially even detectable by the upcoming James Webb Space Telescope. So it's really exciting that the legacy of people like Hawking and Penrose and Dennis Sharma, Martin Rees, Donald Lynden-Bell. So all these people in physics and astrophysics have been working on understanding black hole growth and fueling how they grow, and so it's been really exciting to build upon that and to come up with an entirely new channel to make sort of the first generation of black holes.
So it sounded from what I read in your work that you also suggest that they eventually stop growing. What happens then?
That was a question that always intrigued me when I started working on black holes during my PhD. So when black holes become extremely massive, they can actually stunt their own growth. And the way this works is, as matter falls into a black hole, it gets sped up. So if you can imagine a gas packet that's falling in, it gets sped up, it gets heated, and it starts emitting in the X-rays. And now the glow from X-rays, if the feeding rate is high enough, could be so strong that it could disrupt further inflow. And so the black hole could simply stunt itself. And if you actually do the basic physics calculation, you realize that you can obtain an upper mass limit for black holes at any epoch.
If we're going to think about some of the things that Hawking leaned toward, it sounded like he liked the idea of a multiverse.
One idea in physics that's become popular among some people and anathema to others is that we wanted to explain why the certain constants of nature, so the charges on particles are the way they are, seem to need to be tuned almost to an incredible precision for there to be a universe that would be habitable, that would have the structures that we observe in it. And that seems so miraculous that people said, well, there must be a reason for this. One idea was that, in fact, there are many copies of the universe with, where the charge on the electron is not the opposite of the charge on the proton, but, 2/3 or 5/7. And if that was true, we wouldn't be here. So all of these copies exist. And the fact that one of them happens to have supported life isn't a miracle. It's just like, the tadpole that's swimming around in a little mud puddle and says, isn't it great that, it turned out that there was this mud puddle just right for me and my tadpole friends to be in. And, somebody looking down says, no, look, if you've been born in a drying up puddle or a frozen puddle, you wouldn't be able to survive. So you just happen to be in one of the many possible places where water and sand come together. And that's why you're here. So the multiverse says there are many, many copies of the universe. And the fact that one of them happens to be good physically and chemically for our lives is just the law of averages in some way. So that's one idea. It answers a certain question. Other physicists don't like that. But I think that Hawking's great contribution was really something that Priya mentioned earlier, which is all of physics tells you that if you know the present, you can predict the future or calculate back to the way the past was. And black holes seem to disrupt that idea because if things fell in, you couldn't tell what the world was like. You can't tell from a black hole whether it was made out of pianos or tadpoles or stars or what. So it seems knowing the present doesn't seem to help you figure out what the past was like. And so there's a big debate about this. And Hawking pointed out that this leads to a real contradiction. If the black hole can't really tell how it was made, and eventually he predicted that black holes would evaporate, nothing would be left but heat radiation, then, any information that went into it was gone forever. And that really has bothered physicists. So that problem that he set out in 1974-75 still troubles physicists to today. And Hawking was working on it right up to the time of his death in collaboration with Malcolm Perry, Cambridge, and Andy Strominger, my colleague here at Harvard. And they really have, tried to advance on that problem, try to figure out how there could have been left the information just outside the horizon and avoiding this terrible contradiction that seemed easy.
Priya, what would you add to that?
Like Peter, I have to say that I find the idea of multiverses, going back to multiverses, I find it appealing. So I want to point out that I believe in the multiverse, and the operative word is believe. So it's not clear that it's a testable hypothesis yet. However, I think in 1543, when Copernicus reordered the cosmos, the known cosmos at the time, he could not have predicted that, 450, 500 years later, human beings would set out 2 satellites, Voyager 1 and 2, that could actually leave the solar system, right? So the path of future science is hard to predict. And I'm kind of hopeful and excited at these sort of concepts that seem mind-bending at the moment. And, coming back to Peter's point about Hawking's contribution to understanding the nature of the event horizon and the interior of a black hole, and how black holes could evaporate, that he expected that at the edge of the event horizon you could probably make particles and antiparticles, and those should eventually kind of become radiation that we should be able to detect at some point in the future. So the only problem is that this process of Hawking radiation and evaporation has timescales that are so long for these supermassive black holes that we know that exist. It's much longer than the age of the universe. So the process is not as important. However, for primordial black holes, if there were any tiny, tiny black holes that formed very, very early on in the universe, then they should go zap, and we should be able to detect that radiation. Of course, we haven't found anything yet. And I think, black holes are just enigmatic. Once again, as Peter mentioned, they're tantalizing because they are sort of the limits of our knowledge. They push us. And the whole framework of having order and predictability kind of breaks down. And so I think for me personally, that's what I find really tantalizing about working on black holes and thinking about it. It sort of represents a limit that we would, is a challenge, poses a challenge to physicists and astronomers to push at.
There was something, Peter, that you also wrote in one of your more popular pieces, and it was a quote, I think, from Hawking, where you said the universe appeared spontaneously, starting off in every possible way. What did he mean by that?
Well, this comes back to the question you were asking before about the multiverse and that Priya was addressing. That if you imagined a landscape with many valleys and hills, and then at each of the valleys you could imagine, if you were smooth enough, you could imagine a ball rolling up and down the sides. Well, each of the characteristics, a deep-walled, narrow canyon, a very shallow canyon, the balls would go back and forth at different rates. And you could imagine that as producing something like different particles, because the energy would be different in these different valleys. And each of these valleys corresponds in a somewhat metaphorical, but not entirely metaphorical way, with a different universe. So the idea was that the universe there could be all these copies of the universe with such radically different properties that maybe one of them would correspond to our universe, the one that we have access to. Whether we could ever figure out a way to tell if there was another universe adjacent to ours in some sense is, as Priya mentioned, at this point, just speculation, but that's the idea.
Priya, so let's bring you back in on this. What have you been able to observe and how?
One of the intriguing things, as I mentioned earlier, is you get a lot of physical effects, radiation from the vicinity of a black hole. So gas that's falling in, so lighting up as sources that you would see with instruments that have the capability to detect X-ray radiation. So Chandra Space Telescope, for example, is detecting all these growing black holes strewn everywhere in the universe. So there's populations of them. And so what we have been thinking about and working on is a framework where you start out with these small sort of seed black holes, and then you grow and evolve them in tandem with the growth and assembly of galaxies in the universe over cosmic time, and to see if we can reproduce the kinds of observations that we actually see of assembling galaxies, their central black holes, and the kinds of impact these black holes appear to have on modulating the formation of stars in a galaxy. We believe now that the radiation that comes from the outer regions, well outside, where we're talking about, a million times the Schwarzschild radius or the event horizon. So activity around there, sort of the energy that is produced appears to heat gas and stars. And so there are these sort of impacts, these signatures, invisible kind of invisible activity of the black hole that leaves very visible signatures, detectable signatures have been found. And so the kind of work that we've been doing is sort of build this storyline over entire cosmic history for the assembly of black holes. So for example, there are many, many interesting aspects that we've recently looked into. One of them is, what is the kind of immediate environment that a black hole seed would grow very prolifically? Are there environments where the growth is super boosted? Or is there a limit to how much you can feed a black hole? And so we found that, the environments in which black holes form initially determines their fate. So you can form a direct collapse black hole that tends to form in a very gas-rich environment. So it would grow very, very rapidly. And so it's the most likely ancestor for the super duper massive and ultra massive black holes that we're detecting in nearby bright galaxies.
I thank you very much for joining us here on the Scholar Circle.
Thank you.
Pleasure.
Priya Natarajan is a professor in the departments of astronomy and physics at Yale University. Her publications include Rapid Growth of Seed Black Holes in the Early Universe by Supra-Exponential Accretion and New Observational Constraints on the Growth of the First Supermassive Black Holes. Peter Galison is a professor in the Department of Physics and director of the collection of the Historical Scientific Instruments at Harvard University. He's the author of How Experiments End, Einstein's Clocks, Poincare's Maps, and Image and Logic. He's also the co-editor of Einstein for the 21st Century, His Legacy in Science, Art, and Modern Culture, and the co-director of the documentaries Ultimate Weapon, The H-Bomb Dilemma, and Containment.